This is video number 6 in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. As in the previous video, I'm going to keep the introduction to a minimum really in this for this video. I've got a couple of definitions that I want to start off with, but mostly this video is just going to be theorem based. So I've just got these two definitions really that I need to, three definitions that I need to go through. And then we're just on to theorems. So I've got a few theorems that I'm going to go through in detail, go through the theorem and the proof. But I've got other theorems as well that I just need to state really. I'm not going to go through the proofs. So let's get started on the definitions. The first definition, actually we need to go back to something that we came across earlier in the work. I think it was probably my third video, where I introduced this notation for the class of types. So just a reminder, the class of types is it's the aggregate of all of the ordinal types corresponding to aggregates that have the same cardinal number. So in this case, the cardinal number that we're interested in is A. But we're really interested now in particularly ordinal numbers, not just general ordinal types, but ordinal numbers. Well, we can pick out from that aggregate of ordinal types, from the class of types, we can pick out all of the ordinal types that are actually ordinal numbers and form kind of some kind of a sub-aggregate, a partial aggregate called the number class. So all of the elements of this number class are all of the ordinal numbers that correspond to aggregates that have the same cardinal number, A. In particular, we're going to be interested in what's called the second number class. So the second number class is it's all of the ordinal types that correspond to aggregates that have a cardinality of Aleph naught. We're also going to be interested in the first number class, which is the aggregate of all of the finite ordinal numbers. Presumably, there are the higher number classes, the third number class, fourth number class, but for the rest of the work really, for the rest of this article by Cantor, really it's the second number class that is going to be the main focus. If memory serves me well, there's no mention anywhere of the third number class or anything. It's not specifically. So we're going to be pretty much sticking with the second number class. Notice there is a slight difference between the first number class and the second and the higher number classes, in that the first number class, all of the elements of the first number class are united by their, I guess you could call it their finiteness, the fact that they're all finite ordinal numbers. But they've all got different cardinal numbers because each finite ordinal has its own cardinal. You take two different finite ordinals, they're going to have different cardinal numbers. Whereas with the second number class and the higher number classes, it's a completely different thing that unites them, a different concept that unites them. What unites them is their common cardinal number. So they've all got the same cardinal number. Not that this really plays too much of a role, but it's just something that I wanted to point out really. Just a distinction between the two types of number class. And then we've got the concept of fundamental, coherent fundamental series, or two coherent fundamental series. So this is, I went through coherent fundamental series in my third video in a more general sense when we were dealing with simply ordered aggregates, but now we're dealing with well-ordered aggregates. We've got the same kind of idea. In fact, this is almost a word-for-word definition for fundamental series of ordinal numbers. The only difference is, rather than having the more general symbol between the terms here, which is that, which represents the simple ordering that's defined on the aggregates, we've got the greater than symbol. So this makes sense because we can, these are ordinal numbers, these are series of ordinal numbers, and we can compare ordinal numbers, and we can say that one is greater than or one is less than the other. Whereas in general, with ordinal types, we can't necessarily do that. Okay, so they're the definitions. So now I'm going to move on to the theorems from this section. So these are the first couple of theorems that I'm going to go through from this section. So we've got theorem 15.a. So 15, because what I'm going through, at least in roughly the first half of this video, corresponds more or less to section 15 from Cantor's article. So theorem 15a, the second number class has a least number omega, which equals the limit of this fundamental series of finite ordinals, nu. So this was notation that I introduced right at the end of the last video. So we know that omega is the ordinal number that corresponds to some aggregate, some well-ordered aggregate f0, which effectively looks like this. So it's an ascending series of terms, an infinite ascending series of terms with these relationships between the individual terms. Notice that the cardinal number of omega is equal to Lf0. So that establishes the fact that omega belongs to the second number class, Z Lf0, but it doesn't, we've yet to show that it's actually the least number. So okay, we've got omega is at least in the second number class, but now we need to show that it's the least number in the second number class. Well, let's see what happens if we choose some gamma, some ordinal number gamma, which is less than omega. So if gamma is less than omega, then there must be some segment of this aggregate f0, which will be a well-ordered aggregate itself, which will have the ordinal number gamma. But what do the segments of f0 look like? Well, if we've got the segment A, for example, then it must have the form f1, f2 to f nu for some particular value nu. But then if I consider the ordinal number of this segment, then it's going to be finite. But I chose A specifically so that it had the ordinal number gamma. So that means that gamma is equal to nu, and therefore gamma must actually be finite. So any gamma which is less than omega must be a finite ordinal number, and therefore gamma must be actually in the first number class and not the second number class. So omega must be the smallest number in this second number class. And that's the end of the proof of that theorem. Theorem 15b. If alpha is any number of the second number class, then alpha plus 1 follows alpha as the next greater number of the same number class. So let's take f to be a well-ordered aggregate with ordinal number alpha. Then with alpha being a number of the second number class, then the ordinal, the cardinal number of alpha is going to be Lf0 by definition, really, of alpha, which means that the cardinal number of f is also going to be Lf0. So now let's form the union aggregate fg, where g is just some other element that is not already an element of f. Then by the way that addition is defined, the ordinal number of the union aggregate fg is just going to be alpha plus 1. And we can also easily see that f is a segment of, at least is similar to a segment of the union aggregate fg. In which case, going by what we've got here, that means that the ordinal number of f, which is alpha, must be less than the ordinal number of this union aggregate fg, which is alpha plus 1. So that's not really much of a surprise that alpha is going to be less than alpha plus 1. But we need to show that alpha plus 1 is actually in the same number class, in the second number class. And we also need to show that there is no ordinal number between alpha and alpha plus 1. This last bit might seem obvious because we're used to the idea that if you add 1 to a number you get to the next one, but I've emphasized this point before. These ordinal numbers are really conceptually very different to the usual everyday numbers that we think of. They're aggregates. First and foremost, they are aggregates. So we can't just assume the behaviors that we expect from normal numbers that we use in everyday life, that those properties transfer over to these ordinal numbers. We do actually have to prove these seemingly trivial facts. So let's have a look. Can we show that alpha plus 1 is actually in the second number class as alpha? It's not too difficult to do. If we look at the cardinal number of alpha plus 1, what I'm hoping to see is that this is going to be LF0. So this is going to be alpha, the cardinal number of alpha plus 1. Notice there is a slight difference in the interpretation between the alpha plus 1 and the alpha plus 1 here. So here, ignore the line above, then it's alpha, the ordinal number alpha, plus the ordinal number 1. Then we take the cardinal number of the whole thing. Whereas here, it's the cardinal number of alpha plus the cardinal number 1. So there's a slight difference in what is meant here. It doesn't make too much difference to the argument, but it is just an observation that's worth making. And we know that the cardinal number of alpha is equal to LF0. But what I showed, I think it was the second video that I made, that LF0 plus 1 is just equal to LF0. So what we see then is that the cardinal number of this ordinal number alpha plus 1 is LF0, so therefore by definition alpha plus 1 is going to be in the second number class. We've still got to show that there are no other ordinal numbers between alpha and alpha plus 1, so that's our next job to do that. This is not too difficult to do. Let's say that we've got a gamma, some ordinal number that is less than alpha plus 1. Then there must be, because gamma is less than the ordinal number of this union aggregate, there must be some segment of this union aggregate which has the ordinal number gamma. So either that segment is going to be f, or it's going to be itself a segment of f. So if we've got gamma is equal to the ordinal number of f, if f is the segment that we're interested in, then this is equal to alpha. So in that case we get gamma equals alpha. If on the other hand the segment that we're interested in is actually a segment of f, so we've got gamma is the ordinal number of some segment of f, a, then because a is a segment of f, then its ordinal number is going to be less than alpha. So this comes from the definition of less than with reference to ordinal numbers. So I think it was the beginning of maybe the last video that I did, where I went through ordering of ordinal numbers. So in this case we're going to get gamma is less than alpha. So therefore in this case gamma is equal to alpha, in this case gamma is less than alpha, but it's certainly not between alpha and alpha plus 1. So if I choose any ordinal number that is less than alpha plus 1, then either it's alpha or it's less than alpha, but it can't be between alpha and alpha plus 1. And that finishes the proof of this theorem. Okay, so the next lot of theorems are, well, some of them at least are written on the board here, which I'm going to go through one at a time. Theorem C and D, I'm going to go through in a more kind of informal way rather than writing out their full statement. I'm going to just explain the theorem. I'm not going to prove them. The only one that I'm going to prove here is actually this one here, F. So theorem C relates to fundamental series of ordinal numbers. So if we take a fundamental series of ordinal numbers from the numbers are from the first or the second number class, so it could be a mixture of both, it doesn't make any difference, then what we can say is that the limit function, the limit ordinal, and remember this by what we saw in the previous video, this is a definite ordinal number in and of itself, this limit ordinal. Well, it's going to be the next greatest number after all of the alpha nus. So that's not new to us. What is new to us is that this is going to belong to the second number class. So this limit ordinal, which I emphasize again, is itself a definite ordinal, is going to belong to the second number class. So what this theorem is saying is that if I take any fundamental series of ordinal numbers in the first or second number classes, I can't use it to kind of burst out or break through into the next number class. To do that, I'd need to use different methods, different techniques, but fundamental series within the first or second number class are going to lead me really to ordinals only in that second number class. Even if I take a fundamental series of numbers from the first number class, that's going to take me into the second number class as well. Theorem 15D relates to coherent fundamental series, particularly their limits. So if I've got two fundamental series of ordinal numbers, alpha nu and alpha primed nu, then, so these are my fundamental series, their limits, the limit of alpha nu is going to be equal to the limit of alpha primed nu if and only if these fundamental series are actually coherent. Alpha nu is coherent with alpha primed nu. This is going to be something that is going to be used when I come onto this theorem 15F. It does turn out to be quite a useful little theorem, so I'm not going to go through the proof of it, but the result of this is an extremely useful thing, because it turns out to be useful to take coherent fundamental series and deduce the limit of a fundamental series actually from a different one that happens to be coherent to it. Theorem 15E, so if alpha belongs to the second number class and nu naught is finite, so in other words nu naught is a number from the first number class, then nu naught plus alpha is equal to alpha, and alpha minus nu naught is equal to alpha. So a finite number plus some transfinite number is just going to be the transfinite number basically just eclipses the finite bit, and it just disappears, and we just get the transfinite bit. Okay, theorem 15F. So if nu naught is finite, then nu naught times omega. Remember, omega is a particular number, so it's the least number of the second number class, as we saw in theorem A. So nu naught times omega is equal to omega. So here, if we think of nu naught times omega as nu naught times the limit of the fundamental series made up of the finite ordinal numbers, then using the properties that that I showed in the previous video, this can kind of be brought in here. So I get something like that. So it's the limit of nu naught times nu. And notice also that the fundamental series nu naught nu is coherent with the fundamental series nu. So each of the ordinal numbers multiplied by some finite, each of the finite ordinal numbers multiplied by a particular finite ordinal number, nu naught, that sequence of numbers, ordinal numbers, is coherent with the sequence or series of numbers of just the normal ordinal numbers themselves. So therefore, using this theorem 15d, I know that the limit of this is nu naught omega. That's what we see here. And the limit of this fundamental series is omega. So if these fundamental series are coherent, then their limits must be equal. And that's what we needed to show to prove the theorem. And then finally, at least for this little section, 15g, if alpha belongs to the second number class and nu naught is finite, then alpha plus nu naught all multiplied by omega is equal to alpha omega. So I'm not going to prove that one, but this is another one that uses this theorem 15d. So it effectively finds two coherent fundamental series, one of which you know the limit, and therefore if they're coherent, you actually know the limit of the other one as well. So there's a good few theorems there. I've still got a few more theorems to go through from this section, but I'm going to leave these ones there and move on to the next bit now. So let's have a look now at Theorem H from section 15 in Cantor's work. So if alpha belongs to the second number class, then the totality of ordinal numbers alpha primed of the first and second number classes less than alpha form in their order of magnitude a well-ordered aggregate of type alpha. So the start point here is to choose a well-ordered aggregate f, such that the ordinal number of f is alpha, and let's say that f1 is the lowest element of f. So with it being a well-ordered aggregate, it's got a lowest or a least element. Okay, and then we're going to choose some alpha primed less than alpha. So alpha prime is obviously going to be an ordinal number less than the ordinal number of f, and therefore there must be a segment a primed. So f is a segment of f with the ordinal number of a primed equal to alpha primed. And also, conversely, every alpha primed less than alpha determines a unique segment a primed of f. Okay, so this gives a kind of one-to-one relationship, a one-to-one correspondence between the elements of our aggregates, this alpha primed, the aggregate with all of these alpha primes in, and not f, but the segments of f. Because every segment of f determines a particular ordinal number. And remember that this, within, if I take a segment of a well-ordered aggregate, there are no other segments within that well-ordered aggregate that are similar to that segment that I've chosen. So if I choose the segment A primed of F, there are no other segments of F that are similar to that. In other words, there are no others that have the same ordinal number. So therefore, every ordinal number less than alpha corresponds to a unique segment of F, and every segment of F, it's going to be a one of a kind, so to speak, will determine a unique ordinal number less than alpha. So this gives a one-to-one correspondence between the segments of F and these ordinal numbers less than alpha. But really, I'm wanting a one-to-one relationship between, a one-to-one correspondence between this aggregate and some other well-ordered aggregate, which the aggregate of segments of F, well, it just seems a bit confusing, a bit overly complicated. But fortunately, every segment of a well-ordered aggregate is determined by a particular element. So let's say that we choose A primed, a segment of F, which is determined by an element F primed of F. So obviously that means that F primed has to follow F1. So the initial element of a well-ordered aggregate doesn't determine a segment. We've always got to choose an element that follows that initial element, or is of greater rank. And let's choose A primed, and this is determined by F primed of F, and similarly F primed follows F1. So now let's have a think about this. Let's assume that F primed precedes F primed. Then that means that the segment A primed is smaller than the segment A primed. So okay, these look similar, but that is that's the simple order that's on the aggregate F, and this is the less than. A primed is less than A prime, just to make it clear. Okay, well, let's say that the order type, the ordinal number of A primed is alpha primed, and the ordinal number of A primed is equal to alpha primed. Well, that means that alpha primed is going to be less than alpha primed. So since these elements uniquely determine segments, F primed and F primed, then rather than thinking about this as a correspondence between segments of F and the elements of our aggregate, I can think about it now as a correspondence between the elements of some of the elements of F and the elements of our aggregate instead, this alpha primed and alpha prime. Not only that, it preserves the ordering. So if F primed precedes F primed in F, then alpha primed is going to precede, or is going to be less than alpha primed. So this is the ordering. So the ordering that we place on this aggregate is just their order of magnitude. So in other words, less than or greater than, for example, rather than just the more general simple ordering symbol. So we've got a one-to-one correspondence that preserves the ordering of the elements, but there's a little catch here. It's not a one-to-one correspondence between this aggregate and F. It's actually a one-to-one correspondence that preserves ordering between, if I form the union aggregate of F1 and F primed, so this is all of the elements of F not equal to f1, then my one-to-one correspondence is actually between this aggregate and this part of f. So I can say that f primed is similar to my aggregate alpha primed, but with this being a well-ordered aggregate, f being a well-ordered aggregate, that means that f primed is a well-ordered aggregate. Any part of a well-ordered aggregate is itself a well-ordered aggregate. So therefore these have ordinal types. So because they're similar, they're going to have the same ordinal type. And not only will these have the same ordinal type, they'll actually be the same ordinal number because they are well-ordered aggregates. So the question now is, what is the ordinal number of this thing here? Well, it's going to be alpha minus 1. But now think about the theorems that we proved a few minutes ago. If I've got a number of the second number class, and I subtract from that a finite number, then I just get the number from the second number class. In other words, subtracting a finite number from a number that's in the second number class doesn't really make any difference. So therefore, the ordinal number of f primed of f primed is equal to alpha, and therefore, because these have the same ordinal number, that means that the ordinal number of this must be alpha, which is exactly what I needed to show, that it's a well-ordered aggregate of type alpha, and that finishes the proof. Okay, so the next lot of theorems here, just the two theorems I and k. There is no theorem J in Cantor's work for whatever reason, I don't know. But theorem I, fairly straightforward one. The aggregate that we've just been studying in Theorem H has cardinal number Lf0. It's really easy to show this because we know that the ordinal number of this aggregate is alpha, and we know that the cardinal number of alpha is Lf0. So therefore our aggregate has cardinal number Lf0, so therefore it is definitely a number in that second number class. And then theorem K, every number alpha of the second number class is either such that it arises out of the next smaller number by the addition of 1, or there is a fundamental series of numbers of the first or second number class with alpha as the limit of that fundamental series. Now these are quite important points. I'm not going to prove this theorem, but this is what's called the first principle of generation of the numbers of the second number class, and this is called the second principle of generation of the numbers of the second number class. So this exhausts all of the possible ways of obtaining numbers in the second number class. In fact, these principles of generation of the numbers is enough to carry you through all of the number classes, not just the second number class, but we're really concentrating just on the second number class here. And also numbers that are obtained in this particular way, so using the first principle of generation, are called numbers of the first type, and numbers that are obtained in this way, using the second principle of generation, are funnily enough called numbers of the second type. And this will these different types of numbers we'll have to take into consideration in the rest of the work. There is also a third principle, but it's got really nothing to do with generating new numbers. It's more to do with being able to classify numbers into the second number class or the third number class and things like that. So we don't really need to worry about the third principle. It's not a principle of generation of numbers, so it's more a principle of generation of number classes, I guess. Okay, so I'm going to finish this video there. So we've gone through quite a lot of theorems there. In the next video that I'm going to do, there's going to be a few more theorems for me to go through. But I want to thank you for watching this video, and I look forward to seeing you in the next video.